The image arrived without ceremony, a soft exhalation of data whispered down from one of the coldest instruments ever built by human hands. On the screen, amid the meticulous geometry of pixel arrays and calibration marks, a faint blot of crimson light waited, small, spectral, almost shy. Yet in that unassuming patch of data, framed by ancient noise, lay the single most audacious challenge the universe had yet thrown at us. That was the moment. The first raw cut from the James Webb Space Telescope's NIRCam of a target listed simply as Jades JWST. To most eyes, it was nothing. A smudge, a statistical ghost poised at the edge of detectability. But to the members of the JWST team, veterans of countless false dawns and receding horizons, something about the shape, the spectral slope, the improbable steadiness of that red glimmer ignited a hum that ran through the room like current through a superconducting wire. The data stabilized, the background subtraction held. Photometric redshift estimates climbed relentlessly higher, 10, 11, 13, for a heartbeat disbelieving silence. Then came the whispered number that seemed to stall time itself, 14.32. Redshift 14.32. It meant the light had begun its journey only about 290 million years after the Big Bang. In cosmological language, it was infancy itself, an epoch when the first atoms still struggled to assemble, when the cosmic fog of hydrogen had barely thinned enough to let starlight travel freely. The universe then was less than 2% of its present age. Every training, every model, every cautious line in the textbook said the same thing. Galaxies at that age could not exist in this form, not yet. Gravity had not had the time to gather enough mass, cooling flows had not arranged themselves, metals had scarcely formed. The early cosmos was supposed to be a dim ocean of neutral hydrogen, dotted perhaps with sparse, primitive points of light. This structured, luminous source at redshift 14 should have been impossible. Until that night, the record belonged to GNZ 11. Redshift 10.6, roughly 400 million years after the beginning. Even that detection, made years earlier by Hubble and later refined by Webb, had already strained theory nearly to breaking. GNZ 11 appeared more massive, more organized than any simulation permitted so soon after the Big Bang. Astronomers had stretched parameters to their limits, invoked intense starbursts, exotic feedback suppression, anything to make the timeline hold. But redshift 14, another 70 or 80 million years closer to origin, cut those margins to shreds. Within hours, NIRSpec was tasked to confirm the photometry. The prism spectrum emerged, fragile as lace yet unambiguous. It was there, the Lyman alpha break cleanly observed, followed by a sequence of emission lines whose very presence seemed to ridicule expectation. Oxygen, faint but real. Neon, even hints of ionized carbon. Metallicity that had no right to exist 290 million years after time's ignition. The community would later debate calibration, scrutinize noise models, invoke the devil in the details of cosmic variance. But for those first who saw the pipeline output, the conviction was instinctive and gut level. This was not a mismeasurement. Jades JWST was exactly what it claimed to be. And then, as the composite images deepened with longer exposures, structure began to resolve. What had been a blot became a form. Luminous arms unfurling around a compact, radiant core, hints of a bard's spiral morphology, delicate and defiant. Dust lanes carved through its light, partial but distinct. The spectral energy distribution suggested mature star formation. Sustained and efficient, not a brief flare of population III fire, but an established stellar ecosystem tens of millions of years old. By luminosity alone, it rivaled galaxies several times older. Its inferred stellar mass exceeded 1 billion suns, and still the models sagged, unable to reconcile the mathematics with reality. The canonical hierarchy of growth, the framework of cold, dark matter halos merging step by step over hundreds of millions of years, crumbled beneath that single, stubborn spectrum. Standard cosmology predicted a steep decline in such massive systems beyond redshift 10. Simulations of the early universe, even those pushed to the extremes of resolution and exotic feedback parameters, produced only sparse, irregular clusters of young stars by redshift 12 at most. A structured, luminous spiral at 14 was not just rare, it was theoretically forbidden. Yet there it was, painted across the detectors with brutal clarity, unbending to disbelief. The team checked every known source of error, instrumental artifacts, data reduction missteps. Gravitational lensing magnification. Nothing accounted for the magnitude or the spectral coherence. The lines stood, sharp as carved glass, against the cosmic continuum. One by one, the implications unfolded like dominoes through the fabric of modern astrophysics. Star formation efficiency, baryon cooling thresholds, dark matter halo assembly times, feedback from supernovae and black holes. Each assumption bent out of its expected range until the modeling code collapsed in contradiction. It was, in every sense, an impossible galaxy, and impossibility in science is the birthplace of revolutions. Within weeks, theorists mounted their counteroffensives. Perhaps the primordial density fluctuations were stronger than the cosmic microwave background implied. Maybe the seeds of structure had been amplified by unknown physics in the inflationary epoch. Or the first stars, the legendary population Roman 3, had been far more massive and short-lived than even our wildest estimates, pumping metals and ultraviolet radiation into space at rates that accelerated subsequent generations. Others turned to more radical speculations. Direct collapse black holes forming at absurd efficiency, collapsing primordial clouds birthing compact objects that served as gravitational anchors around which galaxies could congeal almost instantly. And still, there were voices whispering that something even deeper might be wrong, that our understanding of how light stretches with expansion could require revision, that perhaps new physics at the dawn of structure was hiding in plain sight. But in those early May nights of 2024, before the conferences and preprints, before doubt and defense entrenched, all that existed was the image itself. A pale, crimson spiral etched into the oldest light we can see. The signal of order arising far too soon, mocking our timelines, rewriting the thresholds of possibility. We stared into that red smudge and met a younger universe than any we had ever known. It looked back with quiet, unblinking confidence, as if to say, everything you thought was too early had already happened long ago. The deeper the analysis went, the more the cracks spread through the edifice of cosmic theory. Each layer of cross-check only sharpened the contradiction. The first assault fell upon mass assembly. The cold dark matter paradigm prescribes that gravitational wells take hundreds of millions of years to accumulate enough baryonic matter to ignite sustained star formation. Even in the most aggressive simulations, galactic halos massive enough to host 1 billion solar masses of stars could not appear before 400 or 500 million years after the Big Bang. Yet Jade's JWST stood defiant at merely 290 million. Luminous, mature, its gravitational structure already sculpted and stable. If the models were correct, the density fluctuations at that scale should simply not have had time to grow. The primordial matter field, a Gaussian sea of tiny perturbations imprinted upon the microwave background, should still have been too smooth. Only on the smallest scales could overdensities reach the threshold for collapse, producing diminutive, irregular clumps of stars, not a coherent spiral. For a halo to emerge this massive so quickly, its initial fluctuation must have been tens of standard deviations above the mean. Statistically, the odds were infinitesimal, so small that finding even one such galaxy in the survey volume verged on impossible. And yet we had found not one, but several cousins lurking in Webb's deep fields. Next, luminosity challenged physics itself. Star formation leaves fingerprints in the ultraviolet, and Jade's JWST burned with the intensity of a billion suns condensed into a space a few thousand light-years across. Converting that brightness into star formation rate implied close to 30 solar masses of new stars every year. But with such furious birth would come equally furious feedback, winds, radiation pressure, supernovae, all phenomena that should have blown apart the halo before it grew further. The equations of feedback equilibrium no longer balanced. Somehow this object had sustained a stable, regulated cycle far too early, as though nature had leapt ahead to a stage of galactic maturity by pure will. Then came metallicity, the quiet killer of orthodox theory. The Nurspec prism, as unrelenting as truth itself, revealed oxygen and neon where there should have been only hydrogen and helium. These metals are the ashes of stellar generations. They require births, deaths, and recycling of matter over cosmic time. Their mere presence meant multiple rounds of star formation and supernova enrichment had already occurred. By all calculation, there had not been enough time since the first atoms combined to allow such a furnace to ignite, burn, and reforge itself. Finally, structure delivered the finishing blow. Gravitational torques, Those graceful, invisible hands that sculpt disks, arms, and bar formations operate slowly. Angular momentum needs eons to redistribute, yet Webb's imaging showed a coherent, if embryonic, spiral. Dust traced its form like breath upon glass. For a system scarcely 300 million years after creation, such organization was almost surreal. Thermodynamics itself seemed defied. Jade's JWST was not supposed to be awake yet. And worse, it was not alone. Within months of its identification, parallel deep surveys unearthed more redshift 13 and 14 candidates. CERS, GLASS, UNCOVER, each whispered similar anomalies. The dawn of cosmic structure was no modest rise from simplicity, but a violent explosion of complexity, galaxies blooming across spacetime like sparks in dry grass. The age of cosmic adolescence had begun before the universe even learned to crawl. Theorists faced with this expanding evidence marshaled four great explanatory camps, each grasping for coherence at the edge of sense. The first argued for stronger primordial fluctuations. Perhaps the tiny wrinkles in the early universe were not as gentle as inferred from the microwave background. Some mechanism in inflation, a field ripple, a hidden coupling, could have seeded over densities far denser than expected, producing rare, massive halos earlier than probability admits. If so, the map of structure formation must be redrawn, the timeline of clustering compressed by half. But this demanded a re-engineering of inflation itself, that strange period when space expanded faster than light, leaving its frozen fingerprints in the pattern of galaxies we now observe. The second theory turned toward stars, those primordial colossi we call population Roman 3. Simulations had always suggested that the first stars were enormous, hundreds of times the sun's mass, forming from pristine hydrogen and helium. Such behemoths burned briefly but ferociously, collapsing within a few million years. If they were more frequent, more massive, or more efficient at triggering subsequent generations than assumed, they could, in principle, jumpstart chemical enrichment and build large galaxies early. But evidence for those first stars remains spectral smoke. We have never seen one directly, and invoking them in such abundance bordered on cosmic desperation. The third contender looked darker still, direct collapse black holes. Envision ancient clouds of gas collapsing not into stars but directly into black holes thousands of times the sun's mass. These seeds could, through their tremendous gravity and energy outflows, accelerate assembly of surrounding material, birthing galaxies around embryonic quasars. Such engines could illuminate the early universe and explain the fast-growing supermassive black holes already known at redshift 7. But the efficiency required to sculpt Jade's JWST stretched even this exotic mechanism to its edge. And then, standing slightly apart, a fourth idea, an unsettling whisper that perhaps our physics of the early universe is incomplete. Maybe cosmic expansion behaves differently at extreme youth. Maybe dark matter interacts in ways we have never imagined, or light itself warps under conditions we cannot reproduce. New physics, a phrase half prayer, half surrender. It signified that our instruments had crossed a line where data outpaced theory, leaving human understanding lagging behind cosmic truth. Through it all, Webb continued to watch. Each photometric band, each spectroscopic slice, poured more evidence of mature complexity into our archives. More galaxies emerged, each one rewriting the age of structure a little earlier, each one amplifying the absurdity until the term anomaly sounded naive. At redshift 13.2, another compact disk shone as brightly as a present-day dwarf spiral. At redshift 12.6, a dusty starburst hid metals nearly equivalent to the Sun, S. The dawn no longer looked like a slow brightening but an abrupt ignition, an epoch we now call cosmic spring, when the cold fields of hydrogen suddenly blazed into galaxies everywhere we looked. For astrophysicists who had spent lifetimes tracing the slow arithmetic of cosmic evolution, the revelation struck with both awe and unease. Every ratio, every constant, every simulation parameter had been tuned to match a universe that evidently never existed. The cosmos, it seems, learned efficiency we had never credited it with. It built galaxies the way gravity breathes, naturally, urgently, without regard for our equations. In seminar halls and midnight offices, models were broken and rebuilt. Baryon fractions were pushed upward, halo merger rates accelerated. Still the fits failed. Observers turned to the stars themselves. Perhaps stellar evolution was faster under primordial conditions, perhaps radiation pressure behaved differently in metal-free gas. Each fix bred new contradictions. And through it all, the image of Jade's JWST remained. Its light silent but indomitable, testament to a truth human reason struggled to frame. It reminded us that the universe is not obliged to obey our expectations. It writes its script in hydrogen and gravity, not in our equations. And sometimes, when our tools become sharp enough, the cosmos allows us a glimpse of how inadequate our assumptions truly are. The data from Webb alone could no longer suffice. The call went out to every instrument capable of listening across the infrared void, to ALMA, to the great radio arrays, to the telescopes that trace millimeter light from dust and molecules. Confirmation would be absolute, or the foundation of cosmology would continue to crumble upon uncertainty. ALMA answered the call from a very different sky, listening not to starlight, but to the faint murmur of dust and molecules stirred into existence by those impossible early generations of stars. When its arrays turned toward the coordinates of Jade's JWST, the expectation was modest. Perhaps no signal at all, perhaps only a whisper of continuum barely rising above the noise. What emerged instead, after painstaking integration and calibration, was something far more unsettling. A detectable glow of dust emission, tenuous yet real, hinting at a galaxy that had already lived enough lives to forge solid grains from the ashes of dead suns. Dust is the refuse of stellar mortality. It forms in the cooling envelopes of dying giants and in the expanding debris of supernovae. For that dust to be present in measurable quantities less than 300 million years after the beginning demanded not just one generation of stars, but several, born, burning, exploding, and seeding their surroundings with heavy elements. The timeline was compressed to the point of absurdity. Processes once thought to require 500 million years had been crammed into barely half that span. ALMA's receivers probed the submillimeter regime for the fine structure lines of ionized carbon and oxygen, the delicate transitions that trace cool gas and nascent star-forming regions. Even marginal detections or stringent upper limits at that epoch became profound statements. They indicated that not only stars, but the interstellar medium itself had already differentiated into phases, ionized regions, neutral gas, and molecular clouds, all arranged within a gravitational potential deep enough to bind them. The early universe in this tiny corner had already reached a level of chemical and structural sophistication once reserved for far later cosmic times. As these measurements accumulated, the isolation of Jade's JWST dissolved. It ceased to be a lone outlier and instead became the brightest member of a nascent family. Across multiple Webb fields, in survey after survey, a pattern emerged. Compact, intensely star-forming galaxies at redshifts 13 and beyond, each one burning through gas with ferocious efficiency, each one carrying signatures of rapid enrichment and surprising order. What had seemed an individual freak of nature was revealed as the crest of a hidden wave. The statistics grew harder to ignore. One could always dismiss a single galaxy as a statistical accident, a rare fluctuation riding the far tail of a probability distribution. But when the catalog expanded, Jade's JWST, Jade's JWST-12-something, and others from independent programs, the argument of coincidence collapsed. The early universe was not politely ramping up structure formation, it was erupting with it. Number densities of bright galaxies at these redshifts overshot theoretical predictions by factors of 10, in some regimes by 100. That was not a tuning issue, it was a categorical failure. With each new candidate confirmed, the story of cosmic dawn had to be rewritten. The era once viewed as a tentative flicker of the first stars now looked more like a sudden ignition, a phased transition in which gravity, cooling, and chemistry conspired with startling speed. The neutral hydrogen fog that filled space, once thought to clear gradually, now appeared to be riddled with blistering bubbles of ionized gas much earlier than expected. Every massive young galaxy at those redshifts became a beacon, capable of carving expanding holes in the cosmic dark, chipping away at the opaque veil that once smothered photons. This is the epoch cosmologists call reionization, the transformation of the universe from a cold, neutral expanse into a transparent, ionized medium through which light can travel freely. For years, models had balanced the contributions of early galaxies, quasars, and exotic sources to this great change. The new Webb population forced that balance off its fulcrum. If galaxies like Jade's JWST were numerous, then stellar light alone might have accomplished the task far sooner and more violently than anticipated. The reionization history of the cosmos began to tilt, its midpoint shifting to higher redshift, its progression steepening into a sharper curve. In response, observational campaigns grew more ambitious. Webb's future cycles planned even deeper, narrower fields to dissect the earliest structures with finer precision, while parallel programs mapped wider swaths of sky to capture rare, hyperluminous examples. Spectrographs were tuned to isolate Lyman alpha emission, struggling to escape through the patchy neutral hydrogen, each detection a signpost of local reionization. Narrow bands targeted oxygen and hydrogen recombination lines, decoding the hardness of radiation fields and the ages of stellar populations. ALMA prepared to trace cold gas reservoirs feeding these galaxies, measuring how quickly they consumed their fuel and whether vast cosmic filaments were already funneling matter into their cores. By capturing carbon monoxide and ionized carbon, it would map the invisible arteries of early star formation. Together, these observatories would triangulate a new narrative. Where did the gas come from? How fast was it transformed into stars? And how did feedback sculpt the surroundings? On the horizon loomed another eye, the Nancy Grace Roman Space Telescope. With its wide field of view and near-infrared sensitivity, it promised to extend Webb's revelations across areas of sky hundreds of times larger. Where Webb carved deep shafts into the early universe, Roman would sweep broad plains. If galaxies like Jades JWST were commonplace rather than freakish, Roman would find them by the thousands, sketching the large-scale topology of cosmic dawn. The filaments, clusters, and voids that formed when the cosmos was still in its childhood. And beyond Roman, still more instruments gathered on the drafting tables of engineers. 30-meter-class ground telescopes would dissect these ancient points of light at unprecedented angular resolution, teasing out kinematics, rotation curves, and the fingerprints of black holes buried in their centers. Radio arrays would listen for the global hydrogen signal, the faint 21-centimeter echo of reionization sweeping through the universe. Together, these instruments would test whether Jades JWST was the herald of a new paradigm, or a herald of something stranger still. Yet even as the apparatus of inquiry expanded, the philosophical weight of that first image refused to lift. For decades, the standard model of cosmology had reigned with quiet confidence. It matched the microwave background, the distribution of galaxies, the supernova distances, the clustering of dark matter. It seemed complete in the broad strokes, leaving only small details and refinements to occupy the next generations. Then a tiny red galaxy, barely more than a smear on a detector, arrived to remind us that the universe does not read our conclusions. The deeper one follows the implications, the more profound the shift becomes. If the universe assembled complex galaxies in a mere few 100 million years, then its capacity for structure, order, and luminous complexity is far greater than suspected. The first billion years cease to be a slow prelude and instead become a drama of accelerated emergence, a compressed period in which the essential scaffolding for everything that followed was already in place. Star clusters, disks, bulges, nascent black holes, enriched gas, dust, all of this not as a late flourish, but as a near immediate consequence of the Big Bang. This forces a reconsideration of what is meant by early and late in cosmic terms. The distinction begins to blur. The cosmos did not idle through its childhood, it sprinted. Gravity wasted no time in pulling matter into islands of brilliance. Chemistry raced ahead, forging the elements necessary for planets, oceans, and the long chain of events that would eventually lead to eyes capable of looking back on that first light. In the glow of Jades JWST, one sees not just a distant galaxy but a statement about the universe itself, that it is more impatient, more fertile, more adept at building complexity than every careful calculation had allowed. The models will catch up. The equations will be revised, the simulations rerun. Parameters will shift, perhaps new physics will be woven into the tapestry, but the fact cannot be unlearned. The universe knew how to make galaxies quickly, and it did so with abandon. When that realization settles, it changes how one contemplates all of cosmic history. The comfortable notion of a long, dark youth, followed only later by bright, structured maturity, gives way to a vision of a universe that surges toward form as soon as the laws of physics permit it. In that surge, the first stars ignite, the first metals form, the first disks spin, and somewhere in the vast cascade of time that follows, beings arise who can read that story written in ancient light. Jade's JWST is a single frame in that narrative, a solitary point of radiance on a screen. Yet within its spectrum lies the revelation that the opening act of the cosmos was not gentle and hesitant, but explosive and swift, a roaring overture compressed into a fraction of the first billion years. And that knowledge hangs in the mind long after the image fades, a quiet insistence that the universe is not only stranger than it appears, but more accomplished, more rapidly, than anyone had dared to imagine. Across observatories, across wavelengths, across continents, the conversation gradually converged on a single admission. Whatever the detailed mechanism, whether amplified primordial fluctuations, an unexpected fury of population III giants, efficient direct collapse black holes, or entirely new physics, the early universe had outperformed every expectation placed upon it. The arguments grew finer, the models more intricate, but the broad outline remained unshaken. The cosmos had discovered how to assemble luminous, chemically diverse, structurally complex galaxies on timescales once thought reserved for the leisurely middle chapters of its history. In that realization, the routine categories of theory began to feel too small. The first option, strengthened primordial fluctuations, would mean that the seeds of structure were written into spacetime itself in a more dramatic way than the cosmic microwave background alone had revealed. Inflation would need retuning, its quantum fields bending more sharply, its noise spectrum richer at the small scales where galaxies like Jade's JWST took root. In such a universe, the great web of dark matter would have condensed faster, its nodes thickening quickly enough to cradle early, massive halos. It is an elegant possibility. No new particles, no broken laws, only a reweighted initial script. The second path places the burden on the first stars. If population III objects formed in dense clusters, far more numerous and more extreme than imagined, their brief, incandescent lives could have drenched their surroundings in ultraviolet radiation and metals, rapidly transforming primordial gas into fertile ground for second-generation systems. In this picture, galaxies like Jade's JWST are the second act of a ferocious opening scene, built atop the ashes of colossi that lived and died unseen. The universe would have begun with a shout rather than a whisper, its first stellar generation igniting a feedback loop that cascaded toward complexity with astonishing speed. The third hypothesis gives center stage to black holes. Direct collapse seeds, bypassing stars altogether, could have emerged wherever massive, metal-poor gas clouds collapsed under their own gravity without fragmenting. These nascent black holes, tens or hundreds of thousands of solar masses each, would have become engines around which matter gathered swiftly. Their accretion disks would blaze, their jets stir and compress surrounding gas, their gravity sculpt the flows that feed them. Galaxies in such a scenario are, in a sense, built from the inside outward, their structure coalescing around dark, radiant hearts that accelerate the entire process of assembly. And then there is the fourth possibility, the one that lingers at the edge of conversations like a distant storm. Perhaps the equations on which all these models rest are incomplete at early times. Perhaps dark matter is not as inert as assumed. Perhaps it self-interacts or couples faintly to radiation. Perhaps the relationship between redshift and cosmic time is subtly altered by effects we have not yet measured. Perhaps new fields, new symmetries, new particles influenced the infant universe and then faded from prominence, leaving only their structural fingerprints in objects like Jade's JWST. In that case, every high redshift galaxy is not merely an astrophysical puzzle, but an experimental probe of fundamental physics. Whichever of these avenues proves closest to the truth, the consequence is the same. The first billion years of cosmic history must be recharted. The traditional narrative in which a long, dim interval slowly gives way to modest star formation and only later to grand spirals and massive ellipticals can no longer stand unchanged. Instead, the picture hardens into something more dynamic. Within a few hundred million years, gravity has already sketched filaments and nodes across space. Gas has cooled along those threads, falling into deepening wells. Star formation has ignited in intense bursts, enriching and heating its environment, while radiation has begun to carve transparent caverns in the neutral sea. Reionization, once modeled as a gradual and relatively late process, now appears as a faster, more uneven transformation driven by surprisingly capable galaxies. Islands of ionized hydrogen expand around objects like Jade's JWST, overlap, and merge. until the universe is left largely transparent to ultraviolet light. This transition likely completes earlier than many models predicted, with the newly discovered high redshift population supplying much of the required ionizing budget. The darkness of the early cosmos was still real, but shorter-lived and more violently dispelled than the old diagrams suggested. The implications ripple outward. If the universe could generate such complexity so swiftly, then the starting conditions for everything that followed, the later generations of galaxies, the environments in which planets formed, the reservoirs of metals from which rocky worlds emerged, were established under different circumstances than previously assumed. By the time the universe reached 1 billion years of age, the stage was already far more crowded and intricate. Disks had settled, bulges had grown, central black holes had swollen, and the intergalactic medium had been thoroughly stirred and enriched. The later billions of years, including the era in which the Milky Way assembled and the Sun was born, no longer seem like the primary builders of structure so much as refiners of a framework laid down astonishingly early. In this light, Jades JWST and its kin become more than record holders. They are boundary markers in our understanding of what is physically possible. They tell us that the universe had both the appetite and the means to push against every timescale we had assigned to it. Where calculations forecast a slow climb, it chose a steep ascent. Where models expected sparse, primitive clumps, it produced luminous, organized systems with dust, metals, and discernible structure. Standing at this moment in the history of astronomy, one can sense the quiet inversion of perspective taking place. For generations, the first galaxies were treated as distant abstractions, their properties inferred nervously from a few faint points in shallow data. Now, with Webb's mirrors unfolding above the thermal quiet of space, the infant universe steps into focus. Its light is no longer a thin rumor, but a detailed account, a spectrum with lines and breaks and continua that speak of real places, real processes, real histories written when time itself was still young. From here, the work divides. Observers will keep pushing, stacking exposures, chasing redshifts higher, disentangling spectra more finely, mapping the statistics of these early populations across cosmic volumes. Theorists will rebuild their frameworks, incorporating what has been learned, discarding what no longer fits, exploring new forms of matter and new regimes of gravity where necessary. Future telescopes, both in orbit and on the ground, will extend this partnership, using every accessible wavelength to track how the first sparks of order spread through the primordial dark. But whatever refinements come, the core revelation will endure. The universe did not wait patiently to become interesting. It rushed headlong into complexity, forming massive, star-rich, dust-bearing galaxies like Jades JWST when the clock had barely started. It mastered the art of building long before anyone expected, and in doing so, it set the conditions for every subsequent chapter, including the one in which beings arise who can finally read that story in its own light. So the tiny red smudge that first appeared on a NIRCam frame is no longer just a curiosity at the edge of detection. It is a signal from an era when the rules we assumed to be slow and cautious were in fact urgent and extravagant. It tells us that the cosmos is both more impatient and more capable than our best theories had allowed. And when that knowledge settles, it leaves the mind suspended between humility and exhilaration, aware that the true history of the first billion years is only now beginning to be told, and that somewhere in that compressed, incandescent dawn, the foundations of everything familiar were laid down in a burst of creativity far swifter than anyone had dared to believe.